So first of all, thank you to the organisers for the opportunity to speak. I'm very pleased to give you this talk. Okay, yeah, so as Artur said, we'll be talking about the global in time solutions to the n-body Euler-Poisson system, which is a very formal title, so I think I'll take some time at the start of the talk to just explain what the actual physical setup, how you should think about the actual physical setup that is. So this, in particular, this is the compressible n-body Euler-Poisson system. It's multiple balls of gas in space that start off separate from each other and then interact via gravitational interaction, as well as their own internal pressure and their own internal gravity. So what question are we looking to answer in this talk, or what question are we looking to investigate? Well, in the single body case, we found that we can find solutions to the one body problem such that the star expands for all time and the fluid disperses off to infinity. That's work I'll go into more detail for later on in the talk. But that's important because given this family of global in time solutions to the one body problem, you can then ask very naturally, if you have multiple stars in space in some configuration and you set them off to expand in time as you would in the one body problem, can you find a configuration of initial positions for each star and repulsive velocities, that is initial velocities that you give them to try and push them away from each other, such that they will expand and keep moving away from each other, but no two will ever touch in finite time. That work requires an understanding of scaling in the Euler-Poisson system and the gravitational forces between the stars. So that's our situation. Okay, so on to some equations. So as I said, the stars are modeled as balls of compressible gas. As just a convenience point, in the work I'll present, I've taken kappa and kappa dash to be just sort of bookkeeping indices rather than actual, Einstein convention indices. They just count which star you're looking at when you're looking at the system indexed by kappa. So in particular, there's no summation convention over kappa or kappa dash. Use K as an index for any matrices or vectors, but if this particular point has you confused over what an equation means at some point during the talk, feel free to interrupt and ask for clarification. So the system is given by a set of n compressible Euler-Poisson systems in 3 space dimensions and 1 time dimension. Each one has a conservation of mass where rho kappa is the density of the gas, u kappa is the velocity of the gas. It has conservation of momentum, where p kappa is given by is the pressure of the gas, and these systems talk to each other via the Poisson equation, which says that the gravitational potential, which is the same for each star throughout the whole system, is given by Laplace phi is the sum of each of the rho k. So that's how these systems will talk to each other or interact with each other via gravity. And we have the boundary condition that phi goes to 0 as in spatial infinity. Now, on the right-hand side, you'll see these omega kappa of t's, and that's the other very important part of this setup in the sense that we are looking at this system as a free boundary problem. That is, let me see if I can annotate on the, there we are. So in particular, instead of looking at the problem over all of R3 for each system, we set it up so that you have just say, well, in the 2-body case, 2 stars, and then the dynamics are looked at locally in each star, with boundary conditions. So the domain of each ball of gas is given by omega kappa of T, and you'll have some boundary conditions. In particular here, you'll say that the pressure for each star, P kappa, is 0 on the boundary of the domain of the gas, signifying that it is a gas. This weird-looking condition here, all that's saying is that V of d omega kappa of T, which is the normal velocity of the fluid domain, is given by the normal component of the fluid velocity. So all that's saying in words is that the fluid is moved by the gas inside it, which is what you'd expect. And obviously you have some initial conditions for each kappa. So rho kappa, U kappa is given by some functions, rho ring kappa and U ring kappa. Okay, so what's happening here? Is that not? There we are. There we are. Oh, okay, so I should probably get rid of. Let's undo. Yeah, there we are. Okay, yeah, this is basically what I've said in the previous slides. So we have that U kappa, rho kappa, and P kappa are what they are. Omega kappa of T is the closure of the support of the densities, as you'd expect, and d omega kappa of T is its boundary. V being the normal velocity is, as I explained. The one last point I should mention, or not the last point actually, but another important point is that if we just look at the basic equations, we have one unknown given by rho of kappa, 3 more unknowns given by each component in U of kappa, and another one, another unknown given by the pressure P of kappa. But these equations here only give 4 equations, and we have 5 unknowns. So to close the system, we impose an equation of state, a barotropic equation of state. P of kappa is equal to rho of kappa to the gamma, where gamma is some constant strictly greater than 1. This is very common in physics literature or mathematical fluid mechanics literature to describe various gases. Okay, so now we look at something called the physical vacuum boundary condition, and whilst this is very, very important for the basic theory of understanding the free boundary set up to the Euler system and the Euler-Poisson system, I'll hopefully not spend too much time on it, because it would take a lot of time to explain its significance in full detail. In looking at the free boundary problem, where each fluid is supported on a compact body, omega kappa of T, we need, as it turns out, we need some information as to how the speed of sound of each gas in each star behaves at the boundary, in a sense, the right condition to study the free boundary Euler-Poisson system is given by the physical condition, where the speed of sound for a star, in our case, is given by c kappa squared is equal to gamma times rho to the kappa, gamma times rho kappa to the gamma minus 1, which is just the derivative of the pressure with respect to the density. And the physical vacuum boundary condition says that the normal derivative at the boundary initially for the initial speed of sound squared is strictly negative and finite. As I said, this is very important for the basic theory of the free boundary Euler system, but really you should think of it as the boundary experiencing some acceleration as time goes on. So as the system evolves, the fluid is going to push it on, direction, and that push is going to give the boundary some acceleration. Okay, so that's the physical vacuum boundary condition. So some more motivation for it is that actually you can see this behavior at the boundary for some stationary solutions to the Euler-Poisson equations called the Lane-Emden stars, which are stationary radially symmetric solutions to the system studied in classical astrophysics for almost a century or more now. As I said, the fluid vacuum boundary layer experiences acceleration due to the pressure. And what's important mathematically for the system is that this condition here, via a mean value theorem argument, it's not hard to show, is actually equivalent to the fact that the speed of sound squared, which is equal to gamma times rho kappa to the gamma minus 1, behaves like the distance of a point to the boundary near the boundary. And in particular, that has a lot of implications for trying to study or trying to construct a local well-posedness theory, which I'll explain soon. Okay, so I've given you the basic setup. Let's try and go back to some big picture stuff. This basically a rough idea of the theorem that I'm going to try and prove to you in the remaining 40 minutes or so is that given gamma equal to 1 plus 1 over n for some n, some positive integer n greater than or equal to 2, or gamma in the open interval 1, 14 over 13, we can find open sets of initial positions and velocities for each star such that you can set each star off so that they expand for all time, but they never touch in finite time. No two touch in finite time. Okay, so that's a better idea of what we're trying to prove here. Okay, so I assume most of you will probably be familiar with the Lagrangian formulation, or switching from the Eulerian formulation to the Lagrangian formulation with basically method of characteristics. But just as a quick reminder, right now the equations I showed you are in the Eulerian formulation, so that for each kappa, for each domain, you look at the domain as a whole, and then you see and try and see how the domain evolves and the boundary evolves. For our purposes, it's advantageous to switch to the Lagrangian formulation, where instead you define a flow map via an ODE in time for each point x in the initial domain that tracks the particle trajectories from that point for all time. So that's the Lagrangian formulation, basically method of characteristics, and it's what we'll do. For simplicity, you should think of each star, what I will impose is that each star initially is a closed ball of radius 1 with centers such that they're appropriately separated away from each other. So we have a reference domain, which is just the closed unit ball around the origin, and we impose that each domain initially for each ball of gas is given by a translate of the unit ball by this vector x bar kappa, such that all the balls are appropriately separated from each other initially. And so given this imposition, we construct the Lagrangian flow map at each point x in time by solving the ODE. dt of eta kappa is equal to the Lagrangian velocity, that is u kappa precomposed with eta kappa, and that initially, because we're going from the reference domain, which is the closed unit ball at the origin, sorry, there should be a kappa here, there should be a kappa subscript. Eta kappa initially at x is given by the translate of x by x bar kappa. Okay. So now I feel like I should always apologize when I get to this bit of my talk. We'll have to introduce the Lagrangian version of everything that we defined. So here we define the Eulerian velocity, Eulerian density, Eulerian pressure, and the Eulerian gravitational potential. We pull everything back via this flow map, and we get the Lagrangian density, the Lagrangian gravitational potential, and obviously, as we said, the Lagrangian velocity just by precomposing everything by the flow map e to kappa. To present our new system, once we've precomposed the old system with the flow maps e to kappa, we'll need the definitions of the inverse of the change of variables matrix. So grad e to kappa to the -1 is given by a kappa, and the Jacobian is j kappa, which is just the determinant of the gradient of e to kappa. So next, what we'll do is just we'll just shift our viewpoint from density to enthalpy, and the reason we do this is specifically because of this behavior here. So given that rho kappa to the gamma -1 initially behaves like the distance function to the boundary, and this distance function behavior is very important mathematically for the analysis of our system, what we're going to do is instead say that the density rho kappa is not the important quantity when it comes to looking at our ball of gas. It's actually rho kappa to the gamma -1, which is something that we call the enthalpy for each ball of gas. So we define the translated enthalpies, which are just W tilde kappa, which is just the initial density to the gamma -1, but translated so that everything is coming from the reference domain, the closed unit ball around the origin, rather than the initial domains, which are the translated balls. For convenience, we also let alpha equal 1 over gamma -1, so that W tilde to the alpha equals rho kappa. Okay, so given these horrible definitions, what does our system become? It becomes something really, really not nice. So once we pull back our conservation of mass, because of the way we've defined our flow map, in Lagrangian coordinates, it just becomes that the material derivative of something is 0, and in Lagrangian coordinates, that just becomes the time derivative of something is 0. So the conservation of mass is actually that the Lagrangian density times the Jacobian of e to kappa at x plus x bar kappa is just equal to the translated enthalpy. So that if you know the initial density, and if you know how e to kappa evolves, then you can recover your density at time t by just bringing the Jacobian onto the other side and inverting the transformation. Okay, so that was the nice one. Here comes the horrible one. The conservation of momentum is given by this horrible looking thing here. So the velocity term at the start becomes W tilde to the alpha dt squared of e to kappa I, plus this is the pressure term here. This becomes dj of tilde W kappa to the 1 plus alpha multiplied by a kappa ji multiplied by the Jacobian kappa to the -1 over alpha. And the gravitational potential term here, it becomes W tilde to the alpha times a kappa ji times dj psi kappa, where remember that psi kappa is given by it's the Lagrangian gravitational potential. So I'd just like to point out that although this this system is now very horrible looking. What we have done is via the flow map, we've taken a system that we need to solve for rho kappa and u kappa on a moving domain, omega kappa of t, and we've turned it into a fixed boundary, initial boundary value problem, where the unknowns are now eta kappa and dt eta kappa, and so correspondingly, our initial data is now for those quantities eta kappa and dt eta kappa, and the fact that the pressure is some power of the density translates to the boundary condition being that the enthalpy, the translated enthalpy tilde W kappa is equal to 0 on the boundary of our reference domain. Okay, so I said we'd get a horrible system. We did, but actually, you shouldn't worry too much about the specific form of the equation. What you should consider is that the gravitational potential term is lower order in terms of the number of derivatives we take. So instead, let's just concentrate on the velocity term and the pressure term for now to get an idea for what the system kind of looks like. And if we just count derivatives, we have something that looks like dt squared eta plus one derivative acting on just ignore now. This looks like one spatial derivative of eta, and this also looks like one spatial derivative of eta. So to top order in terms of derivative count, what we actually have is something that looks like dt squared minus Laplacian eta, in a sense that very, very roughly it has a wave-like structure, although with two very fundamental differences to the normal wave equation that I'll explain. Okay, so well-posedness for this system. As I said, the physical vacuum boundary condition plays a large role in constructing the well-posedness of the system, in the sense that although we don't have a precise result, the community that works on this free boundary problem for compressible fluid mechanics feels that the physical vacuum boundary condition in the context of Euler, Euler-Poisson, and various Euler adjacent systems is the correct condition to have at the boundary for the speed of sound, because it's the one that says that there should be normal acceleration at the boundary, at the vacuum boundary layer. However, as a trade-off for this, what we actually have is that the speed of sound squared, which is proportional to rho kappa to the gamma minus 1, behaves like the distance function. One in particular, the speed of sound itself is only the speed of sound is only Holder continuous of exponent and a half rather than being continuously differentiable. This provides various difficulties in trying to construct a well-posedness theory. And the other part is that obviously, as we get to the boundary of the domain, because of the boundary condition, we have degeneracy at the boundary, which is again a really an additional difficulty that makes it very, very tough to construct a robust local well-posedness theory for the free boundary compressible Euler system. Nevertheless, in 2010, Couton, Scholar, and Moody independently proved local well-posedness in Lagrangian coordinates. And last year in 2020, Ifrim and Tataru in Eulerian coordinates also constructed a local well-posedness theory. Now this is just for the compressible Euler system in the sense that one, it's only for one body of gas, and two, there is no gravity considered. That was the state of these well-posedness theories. However, for as I say here, for the one body case, the free boundary Euler-Poisson system, you can construct a local well-posedness theory, noting that the gravity term is lower order in terms of derivatives. So all you need are sufficient a priori estimates, which you can find. And if you want more details, see Hadjik Zhang in 2019. So in our case, where there are multiple bodies, local opposedness can be shown similarly to the one body case. All we have to deal with are extra tidal terms, because in the one body case, all you have is the self-gravitation. In the two or more body case, obviously what you'll have is tidal terms wherein there's gravitational attraction between each star. But once again, because mathematically these terms are lower order in terms of derivatives, all you need are sufficient a priori estimates, and then you can piggyback off the constructions in 2010 to find a local opposedness theory for our system. Okay, at the start I said we have a large class of solutions to the one-body Euler and Euler-Poisson system where the star will be expanding for all time. So we should motivate why you would look for expanding solutions first of all. Well, in this Lagrangian formulation, you'll see that now you've switched viewpoints and you're tracking the particle paths, and you'll know that if particle paths cross, your flow map becomes non-invertible, and it corresponds to a shock in the fluid. So if you want a global in time solution, it's very natural to look for solutions where you force the particle paths to move away from each other, and that corresponds physically to an expanding fluid. In the case of a ball. For compressible Euler, there's been a lot of work where we look at trying to find expanding solutions to the free boundary compressible Euler system. Just on the whole space with no free boundary formulation, Denise, Grassan, and Rozanova in 97, 98, and 2003 constructed expanding solutions with there are various drawbacks. So one has velocity exploding to infinity, a spatial infinity. One can't guarantee uniqueness. So there are, in general, drawbacks to try and find global in time solutions for the compressible Euler system without looking at the free boundary formulation. It's very, very easy to form shocks and singularities of other natures. In our case, in the free boundary setup, Sedaris in 2014 and 2017 found global in time solutions to the compressible Euler system, just using what is essentially a separation of variables argument, where he says that he asks that the flow map eta of Tx is equal to a time-dependent matrix field A of T acting on the vector X. Moreover, in 2018, Hadjic and Zhang showed the nonlinear stability of these solutions for the range of gamma strictly greater than 1 and less than equal to 5/3, and later Sedaris and Scholar extended this past 5/3 all the way to infinity. So these solutions are nonlinearly stable. In Euler-Poisson, what we have is that, in fact, what's remarkable is that not only are these Sedaris solutions nonlinearly stable, you can use these Sedaris solutions for compressible Euler without gravity to construct global in time expanding solutions to the Euler-Poisson equation with gravity. And the reason you can do this is because if you assume that you have small density, so small mass at the star, you can treat the gravity term as a source term, and it is essentially. So given these solutions to compressible Euler, you can find solutions to compressible Euler-Poisson. Away from the paradigm of Sedaris solutions, Hadjic and Zhang showed that if you take an ansatz of the form eta of Tx is equal to T plus 1 times x plus theta, you can also find global in time solutions to free boundary compressible Euler and free boundary compressible Euler-Poisson under the assumption well, small theta is what you're trying to prove, but under the assumption of small density. And it should be noted that if we think of theta as a perturbation, t plus 1 times x is not a Sedaris solution, so we are not perturbing away from a Sedaris solution. A of t equaling t plus 1 times the identity will not give you a solution in that case. So really, we rely on the structure of the equation. There's various scaling structures in the Euler system that allow you to stabilize the solution and have global and time existence. So that's work for the family of expanding Bose solutions in when modeling stars. I should just mention that McCann 2006 gave a binary star solution in equilibrium using variational methods. So they're just stars that rotate around each other like this. Okay, so I've colored this X in as red, and the reason I've done this is because the next slide, because what I want to point out is that if you have a ball initially and you want your theta to be small, then what X is doing as both the initial position and what is approximately the velocity for all time is forcing the particle paths to follow an approximately radial path as time goes on, which in the case of the unit ball is exactly what forces expansion of the fluid and what forces the particle paths away from each other so that we avoid shock formation. With this in mind, what we'll do for the n-body system is that we'll say, okay, we still want the bodies to expand for all time, but we would like to repel them away from each other so that this expansion and the gravitational attraction does not lead to 2 or more stars touching in finite time. So taking inspiration from the ansatz, we introduce an ansatz for the n-body case, wherein eta kappa of t is the initial position at time t of x is the initial position, which is just x translated by x bar kappa. And then we have a velocity term, which is given by x in red, which is, again, the expansion that we want in the n-body case as we had in the one-body case, and what we call a repulsive velocity, mu kappa of x, which hopefully will encode directions in which we fling each star at as time goes on, so that they never touch. And then obviously we have once again this error term theta, which we will hopefully show is small for all time. And that's what we say here. Now, as I mentioned, this sort of work requires a small density assumption, in essence, to treat gravity and some other terms as source terms that can be estimated sufficiently. So the small density assumption is that we'll just say that so small tilde w kappa is equal to delta times 1 minus r squared up to the boundary of the domain where it just becomes 0. And we'll say that this 1 minus r squared is given by a large w tilde kappa. So just a point on this, I've just done this for simplicity, but that's actually, there's an infinite dimensional family of large w tilde kappa that can satisfy what we need and is admissible as an enthalpy profile. All we need is that it behaves like the distance function near the boundary, and that on the whole domain, the ratio of w tilde over the distance function is smooth. And so this delta here is what is our small density assumption. This is now a constant parameter that we can just play with, and we'll make as small as possible, and this encodes the small density of each star in our system. So, and just for convenience, we define a new timescale tau, which is equal to log of t+1. There's nothing fundamental or that important about this. It's just that I want to work with exponential time weights rather than polynomial time weights. Okay, so under this rescaling, what we get is that if we say that eta kappa under this definition is equal to e to the tau times zeta kappa at tau x, what we get is all these rescale variables where, you know, a of kappa, curly a of kappa and curly j kappa are now just the same definitions as before, but for the rescaled quantities rather than eta kappa. These rescalings now become these rescalings now give you the system in another form, wherein, so let's go back to this. So once we introduce rescaling to this system, what we get is 1 over delta e to the 3 over alpha tau times by large W tilde to the alpha, multiplied by d tau squared of theta plus d tau of theta, plus this thing that looks like a rescale pressure term, plus on the right hand side what looks like the rescale gravitational potential term. Okay, so let's just have a look at what this system gives us. Well, there are two things that we should note here. There's the power of large W and the power of large W between the velocity and pressure terms are mismatched. There's an alpha here and there's 1 over alpha here. This mismatch, or this scaling, is what allows us to produce a 1 over delta in front of the velocity term here. And this will be incredibly important in closing our estimates by giving us a chance to estimate our source term sufficiently in the right energy space. Moreover, once we rescale in our new time variable, well, okay, so the new time variable isn't so important, but once we put in our new rescale flow map, the mismatch between the velocity term here and the -1 that you get from the inverse of the gradient and the -1 over alpha that you get for the Jacobian produces, again, once you multiply it by the right power of exponentials, e to the 3 over alpha times tau, which is a positive exponential because alpha is positive. And this positive exponential allows us to bound our solution in an energy space which ensures that theta stays all the time. So this delta allows us to estimate source terms, and this e to the 3 over alpha tau allows us to stabilize our solution and make sure that it exists for all time. So our initial data is given by theta kappa is just 0 everywhere initially, and d tau of theta kappa is given by the difference between the Lagrangian velocity and the initial Lagrangian flow map plus mu kappa, where mu kappa was the repulsive velocity. And so once you unwind what this means by remembering that the initial Lagrangian flow map eta kappa at time 0 is just to translate, what this is saying is that your Lagrangian velocity is actually just an expansion term, which is given by the initial flow map eta kappa, and a repulsive term, which is given by mu kappa. So this ansatz takes advantage of the scaling structure present in this system. Gives us exactly what we want, in the sense that if we can prove that theta stays small for all time and d tau theta stays small for all time, we will see that the Lagrangian velocity always approximately looks like an expansion term and a repulsive term, which is exactly what we want. So what I haven't mentioned here is the gravity term, which I've just absorbed into this curly f, and that's what we will look at now. So all the densities have compact support. We can use the fundamental solution to find phi, which is the Eulerian gravitational potential, and therefore by pulling back via eta kappa, the the Lagrangian gravitational potential. So I won't bore you with the calculations, but what we do obtain is that the rescaled Lagrangian gravitational potential splits into a self-gravitational potential and a sum of tidal terms, basically, for each kappa, so this term kappa dash is taken over all kappa dash, which are different to the kappa we're considering. So this is the self-gravitation term, and modulo fancy-looking rescale terms and Lagrangian flow maps and all that. This looks very much like just the Newtonian kernel with some weighting, which is given by the density, as you'd expect. The tidal terms are what are unique to the n-body case, in the sense that this term here really encodes the novelty of the situation we're looking at, in that this encodes the fact that these stars are attracted to each other by gravity. And this last term here is what we'll need to analyze to find a sufficient condition for our repulsive velocities, so that no stars will touch in finite time, because this really is what this term is what we're trying to control. We're trying to make sure that the gravitational attraction between any two stars doesn't blow up. Okay, so that's the gravity terms. Yeah, as I said, the self-interaction terms are familiar. They're investigated in Hadjik Zhang in the context of compressible Euler-Poisson, but anyone who's worked with anything involving gravity will have seen it. The tidal terms are what are unique to this case, and they sort of mimic the right-hand side of the ODE when you look at the n-body system for point particles. But of course, there's a difference here in the sense that these stars aren't point particles. The tidal terms will not just attract the centers of mass to each other, they will also deform the topology of each star. So we have to be careful that we try and avoid any of that happening. Okay, so investigating these terms will give information on the possible geometries of the initial configuration, that is, the configuration of initial positions of each star and initial repulsive velocities of each star. So our methodology is we seek global and time solutions to this horrible looking thing here. We define a appropriate higher order energy function. We will use the bootstrap method on local and time solutions, which is why the local opposedness theory is so important in this case as well. And yeah, the last step of bootstrapping is the continuity of the energy function will give you global and time existence. Our higher order energy function needs appropriate derivatives that we act on the equation with, and that comes from trying to understand how to deal with the degeneracy that comes from the weighted wave equation that we're studying, in a sense, where the translated enthalpies go to zero at the boundary, giving us degeneracy. We do this by adapting the strategy that Zhang and Mahmoudi showed us in 2010 when they constructed their local opposedness theory, in the sense that if we just take the unit ball again and we visualize where this degeneracy is coming from, well, it's only coming when you travel towards the boundary in the normal direction. So the motto, or sort of the moral of the story, is that tangential derivatives are fine. Normal derivatives, you have to be careful. And they consider this and solve this problem by saying that, okay, take all the normal and tangential derivatives of the equation that you want, but when you take a certain number of normal derivatives, you then have to have a weight in front of your energy that combats this potential increasing degeneracy by taking lots and lots of normal derivatives. So, and this is given by the weights on the function space, which is related to the normal number of normal derivatives applied. So we're dealing with lots of unit balls. Well, actually, yeah, our reference domain is just a closed unit ball around the origin. And so what do we want? Well, there's a natural choice of coordinates, spherical polar. What we do is just adjust spherical polar slightly so that we have a nice commutation between lambda our radial derivative, and this d/ij, which are our tangential derivatives. Someone paying attention will point out, look, these derivatives go to 0 at the origin, and yes, that's correct. But as I've said, the degeneracy only happens around the boundary. So if you're looking for a technical explanation as to why we can do this, in reality, what we do is run a partition of unity argument where we deal with these derivatives. We deal with these derivatives near the boundary, and then on the interior of the ball, we can just take normal rectangular derivatives. There are weights in front of the energy function on the interior, but they just come from the natural energy function when you do what you do to get an energy function from a wave equation. They're order 1 on the interior, so there are actually no weights at all. So these derivatives go to 0 at the origin, but we'll only consider them around the boundary. And in fact, I'll only show you the technical stuff around the boundary because the stuff on the interior is very easy. There are no weights. There's no degenerate weights to worry about. It's our higher order energy function. Don't worry so much about the specific form. What I want to point your attention towards is that this is the part of the energy function coming from the velocity term, and because of the rescaling, we get to put a 1 over delta and an e to the 3 over alpha tau dash in front of our L2 norm. And this is what I mean by defining an appropriate higher order energy function, because this 1 over delta allows us to estimate this term here, which is actually lower order, and we just put in for convenience. This 1 over delta via fundamental theorem of calculus argument allows us to estimate this and put a delta in front of the estimate as well as the energy function, giving us the smallest that we need to close our estimates later on. And this e to the 3 over alpha tau means that if this whole thing is bounded by constant for all time, it means that d tau of theta is decaying in some norm, which in sufficiently high, with a sufficiently high amount of derivatives will, via Sobolev embedding, give you that it's decaying in, say, what, C1, C2, and so d tau theta kappa is actually decaying to 0 point-wise everywhere, which is what you want. This is what stabilizes the solution and gives your Lagrangian velocity the correct approximate form for all time. So this is the higher order energy function for each kappa, and so obviously for the whole system we just take a sum over kappa. We need to define higher order curl functions for dt, theta, and I'll explain why in a couple of slides. These come naturally. And then we just have some bootstrap assumptions that say on some time interval we have that the energy function is small, the inverse of the gradient is close enough to the identity, the Jacobian is close enough to 1, and then there's also this sum of L infinity norms of theta kappa, which is small, which is just what you need. It's just a technical thing. So these are just some bootstrap assumptions. And then we also have a small assumption on the gradient of the mu kappa. So it turns out that mu kappa is should be approximately close to a constant vector for each star, repulsing each star away from each other uniformly. This is again just technical, and this is the key to our construction working separation condition, what I call the strong separation condition, which says that any convex combination of the relative initial positions and relative repulsive velocities is sufficiently bounded below. So given all these assumptions, here's the main theorem. So for our range of gamma that we mentioned before, which is again purely technical, don't worry too much about that. Given a solution by local opposeness theory on 0t, if we have the strong separation condition satisfied for a large enough lower bound, there exists delta and epsilon 0 small enough such that small enough initial data leads to a global in time solution with a global energy bound, And in addition, what you get for free there are time-independent attractors for each error function theta kappa, such that theta kappa tau minus theta kappa of theta kappa infinity goes to 0 as tau goes to infinity. Okay, great. Well, I mean, that's very technical. What it says is that we succeeded. We found expanding star configurations such that we can set their initial positions and velocities in such a way that they will keep expanding but never touch infinite time. And so since I'm nearly done, I won't explain too much of the technical stuff. What I will give you is some examples of so yeah, this is just saying everything I've been saying before, in that the Lagrangian velocity, the flow map behave exactly as you want them to because of the smallness of theta and d tau theta. So I'll just give you some examples of solutions. So in the case that you set mu kappa, the repulsive velocity, equal to a constant, and in particular the constant being the center of every star, x bar kappa, your strong separation condition collapses into this very, very simple condition on each initial position. And so, for example, you can get something like this happening. So this is the origin, this is each star expanding, and you just set the repulsive velocities to go on the same paths as if you were drawing a path from the origin to the center of each star. So kind of boring, but it's nice to know that you get a large class of solutions to this system very, very easily. So for something more interesting, we instead look at this triangular configuration and fire each star towards each other in a clockwise manner, or sorry, an anti-clockwise manner as t develops, or the system develops in time. And what you get is that if you let S1 be the star at the top and you name S2 and S3 in an anti-clockwise manner, and you let their centers and repulsive velocities be given by this. Obviously, there should be Z components, but we'll just ignore them because you can just look at it top down. So they're just given by these coordinates here with a positive constant C in front of all of them. Then you can just calculate that this complex combination with the repulsive velocities and the relative repulsive velocities and the relative initial positions is given by this positive thing here, and it's very clear that for large enough C, you will get you'll satisfy the strong separation condition. And yeah, so that's everything apart from technical stuff. I'm not sure if I'm allowed 5 more minutes to go over the technical stuff, or if we want to just end now.
Well, I think we have more 5 minutes if you want to.
Okay, yeah, sure. No, so I'll just go over the technical stuff. It's not in very much detail. Okay, so we're trying to come up with an energy function from our equation, and then find sufficient estimates for our energy function. What we actually find is that although I said the Lagrangian Euler system, the Lagrangian Euler-Poisson system looks like a wave equation, the specific form of the inverse gradient and the Jacobian that arises inside the spatial derivative in the pressure term gives you a nice velocity term, a nice Lagrangian gradient term, and a nice Lagrangian divergence term, but it gives you a Lagrangian curl term at top order with a bad sign. So this is in red, and this will absolutely ruin us if we don't find another way to estimate this quantity. This is a small point. There's a subtle issue to making sure the correct powers of the translated enthalpy appear in the energy function. It's of course related to the correct algebraic structure of the weights in front of a certain number of normal derivatives, as Zhang and Masmoudi said you should have in that construction. But it's a relatively small issue, and it's quite technical, so we'll just skip over it. So yeah, we have to deal with the curl terms, the curl term in red. How do we do this? Well, actually, we can rewrite our system as this velocity term here, d tau squared theta kappa plus d tau theta kappa, plus the Lagrangian gradient of this whole thing. And actually, what's inside the Lagrangian gradient doesn't matter, because what we can do now is notice that curl, the Lagrangian curl annihilates the Lagrangian gradient. So if we just apply the Lagrangian curl to this equation here, what we get is an equation purely in terms of the Lagrangian curl of d tau theta and d tau squared theta. So in essence, we can decouple the dynamics of the curl term from the rest of the equation, and we can use it to get good bounds on curl of d tau theta, and then we can integrate in time to get good bounds on curl of theta. And so this is in essence the sort of inequality that we get for the norm of curl of theta that we've constructed. I should mention that this isn't new; it's not novel. Couton, Scholar, Zhang Masmoudi, Hadjik and Zhang, various other people have noticed this this structure in the Lagrangian Euler system that lets you decouple the curl terms from the velocity terms. Sorry, the curl terms from everything else. Okay, next, as I said, we use fundamental theorem of calculus to estimate norms, the theta norms in terms of d tau theta norms, and it's very easy. And then the 1 over delta in front of the velocity norms lets you put an extra delta in front of the estimate for your theta norms, which is very important. It gives you an extra source of smallness when that we use repeatedly in remainder terms. So I should point out that is that when we try and do energy estimates, we're going to act on this equation with lots of derivatives. And so we have source terms coming from the gravitational potential term, which I've already mentioned. But we also get source terms from acting on the pressure term when all the derivatives fall on W tilde. So W tilde has no smallness. It's bounded, but it will give us no smallness no matter how many derivatives we take. So which makes it a source term when all the derivatives fall on W. And the 1 over delta becomes very important because again, we can instead of finding another way to try and estimate these source terms, what we get is that when doing our final energy estimate, we have the integral from tau 1 to tau of some function that's integrable in tau. So this is our time weight, but the source terms only give us the energy function to the power of a half when we estimate it, would try and estimate in the correct energy space. This, without the delta, would kill us, but thankfully we have a square root delta in front of this integral, which means that we can close our estimates in the following way. We just use Young's inequality on this thing here, and our energy inequality becomes this thing here, which we can close and run the bootstrap argument for. Yeah, and that's everything, I think. Yeah. Thank you very much for your time.